And welcome back. So we're now starting the third topic of this course, which is atomic structure and the periodic table. Now in this first lesson, we're just going to have a recap of what you did at IGCSE about atomic structure. So you may already know this, but certainly by the end of this presentation, you should be able to give basic information about the three major subatomic particles, their position in an atom, relative masses, relative charges. You should be able to work out the number of subatomic particles in a range of atoms and all their isotopes. You should be able to work out the relative atomic mass of elements. Right, okay, so right back to basics. Now, every element has a nucleus. This is the central part of the atom, and it is made up of a cluster of little spheres. Now, these are protons and neutrons. Now, around this nucleus, we have electrons. Now, at GCSE, you did that they orbit in what are called quantum shells. So they are just orbiting in areas of space around the nucleus. So how do we know how many protons, neutrons, and electrons an atom has? Well, let's see if you can remember. Now, I've drawn a nucleus here containing protons and neutrons. Can you see a relationship between these two numbers and the diagram? Just have a little pause and think about it. Hopefully, you either remember or you can work out the relationship between them. So this is actually the nucleus for lithium. And hopefully you'll recognize that these are the numbers you would get with lithium on the periodic table. So, what is this relationship? Now, the small number, I say the small number because depending on the periodic table, the small number can be at the top or the bottom. Here, it's at the top. Now, the small number, this tells us the number of protons that are in the nucleus of an atom. Now, this number on the periodic table is known as the proton number or the atomic number. It's the same thing, it just has two different names. This tells us the number of protons. Now, which element the atom is determined by the number of protons. Okay? And the periodic table is ordered in terms of atomic number. Now, the larger number, again, it can be at the top, it can be above the atomic number or below it. Just depends on which periodic table you're looking at. Now, in this case, it's 7. Now, hopefully you will have noticed that is the total number of spheres in the nucleus. So that's the amount of protons and the amount of neutrons added together. You can see there are 7 spheres in the picture because the total number of protons plus neutrons is equal to 7. So, because the mass number is equal to the number of protons and number of neutrons, okay, and the atomic number is equal to the number of protons, to work out the number of neutrons, we just take the big number, the mass number, and subtract the small number, the atomic number. So it's very, very easy to work out the number of electrons, protons, and neutrons from the numbers on the periodic table. The atomic number is the number of protons. In any neutral atom, number of protons is equal to number of electrons. So for a neutral atom, the atomic number will also give the number of electrons. And then neutrons, it's slightly more complicated, but still reasonably simple. You just take the big number, you subtract the small number, and that gives you the number of neutrons. So let's just give ourselves a little bit more information about these 3 major subatomic particles. Now, each of them has a charge. Now, it's called the relative charge because we're just comparing the charge to the other subatomic particles. It doesn't have units, okay? So hopefully you remember that a proton has a relative charge of +1, an electron -1, and a neutron is neutral, no charge. Now the relative mass, this is important regarding all your calculations, okay? Now protons have a relative mass of 1. Neutrons also have a relative mass of 1. They basically have the same mass. Now electrons don't. They are much smaller. In fact, in terms of mass calculations, you don't even include them. Now technically they do have some mass, and that is equivalent to 1 divided by 1836. Like I was saying, they're so small you don't even include them in mass calculations. Okay, so now we have some information about the free subatomic particles. Let's take it a step further. So, what is the difference between these two pictures? Hopefully you'll recognize Brad Pitt. Is it still Brad Pitt in the second picture? How about this one? David Beckham there. Is this still David Beckham? Morgan Freeman, can you notice the difference between these two? This one's a little bit harder. Okay, you might be thinking, what is he doing? Why is he showing me these pictures? Well, the point was, you can be thinking, okay, it's still the person, but something's different. So, what's the difference? Okay, it's still carbon, but there's a difference. One of the numbers is different. The mass number is different. How about this one? Okay, again, mass number is different. Now, how can we have this? Well, this is linked to something called isotopes. Okay, now most elements in the periodic table have naturally occurring isotopes. These aren't man-made, they exist naturally. So a certain proportion of each of the elements has a slightly different mass number to the rest of that element. So isotopes contain the same amount of protons, so they are the same element. So remember, the actual element itself is determined by the number of protons, but they contain different numbers of neutrons. So they are the same elements, but they have slightly different mass. Now, why is this important? If you look on the periodic table, it doesn't say mass number. It says relative atomic mass number. Now, the relative atomic mass number is often a decimal. Now, we've just been through how a mass number is number of protons plus number of neutrons. How can you have a fraction of a proton or a neutron? Well, you can't. So the relative atomic mass number isn't just counting protons and neutrons. It is the weighted average of all of the isotopes of that element. So how do we actually work out relative atomic mass? Okay, so let's look at chlorine. Now, chlorine exists as two major isotopes. It exists as chlorine 35 and chlorine 37. Now, if we look at the periodic table, you'll see that the relative atomic mass for chlorine is 35.5. Now, if you can't remember how to do this, you might be thinking, well, why isn't the average 36? And that would be a reasonable assumption. But this is a weighted average. Now, naturally, there is more chlorine 35 than 37. So you're taking an average, effectively, of every atom of chlorine on the planet. Okay? So approximately 75% of all chlorine is the chlorine 35 isotope, and only 25% is the chlorine 37. So how do we get to 35.5 from this? Okay, well, it's a fairly simple calculation. You multiply the percentage by the mass number for each isotope, add them together, and because it's a percentage, you divide by 100. Now, if you put this sum into your calculator, it will come out at 35.5. And that is how we get the relative atomic mass number. Now in your examples, you might not be given percentages. You might be given what seem like random numbers, but they're not random at all. They are given the ratio of the different isotopes. So how do you go about doing that if you're given numbers and not percentages? Okay, so if you're given numbers, now, like I said, these numbers may appear random, but they're not. They are a specific ratio. Okay, so how do you go about this? It's pretty similar. So the top part looks pretty similar. Instead of using percentage, you're just using the number. Now, underneath this, before we used 100 because it was a percentage, it was out of 100. However, now I use 16 because it's 12 plus 4. Whatever these numbers are, you just add them up together, and that forms the bottom part of your sum. Now again, put these into your calculator, and you get the same number. So that's the simple calculation for working out relative atomic mass. Now you may still get that in your AS exam, so make sure you can remember how to do this. So hopefully after this quick recap, you should be able to state all the basic information about the three major subatomic particles, you should be able to work out the numbers of subatomic particles, protons, electrons and neutrons, if you are given their atomic and mass numbers, and you should be able to work out the relative atomic mass of elements, whether you're given information as a percentage or as a numerical ratio. So, make sure you complete your notes, and I'll see you in class.